Okay, continuing where we left off on Wednesday. We were looking at Compton scattering. Why were we looking at Compton scattering? And surely it's not because we're going to do experiments with it. Why were we looking at it? Evidence for... No.
Wait, what are you talking about?
Compton scattering. Compton scattering is what Arthur Holly Compton noted when he was scattering very short wavelength light off of crystals. And what he found was that the wavelength of the scattered light, if it went straight, there was just the wavelength he started with. But if it was deviated by an amount, there were two peaks. There was the peak he started with plus another peak that was at a different wavelength. No, not changing energy level. Although in 2 slides, I'm going to have you do a problem where I have you calculate the change in energy. But that wasn't. There's an important purpose for us looking at Compton scattering. We prefaced it last class period with a question about wave model versus particle model. In the wave model, what was true about frequency? The frequency of a wave, if it goes from one material to another, what happens? It stays the same. For the wave model, the frequency cannot change. And the Compton scattering, if the wavelength changes and you're in the same medium, that means the frequency changed too. And so the Compton scattering is showing a change in the frequency, which a wave just can't do. So what's the importance of the Compton scattering? It shows that the light is acting like a particle. Right? We already looked at things that said light acts like a wave, and then we saw first the photoelectric effect, now then X-rays, and then Compton scattering of light behaving like a particle. So with this scattering, you have a photon coming in, and it hits an electron, and then the electron scatters. That means it goes off in some direction, and the light scatters in another direction. And the angle that the light scatters is the scattering angle. So the angle, it deviates from going straight. And it's really hard to tell that's a theta because of the blue line underneath it there. And this here is supposed to be a wiggly line for light. We use wiggly lines for light. And so the key is, light is behaving as a particle here. And so Compton used relativistic equations for conservation of energy and conservation of energy and conservation of momentum to determine what was happening here. And so the photon loses energy when it scatters and goes to a longer wavelength. How do I know it loses energy when it goes to a longer wavelength? What's the equation for the energy of a photon? According to Max Planck. Okay? So if you go to a longer wavelength, you're going to a lower energy. So the photon is losing energy when it's scattered. Where's that energy go? It goes into the particle it bounced off of. So it's going, in this case, into the electron. Now, I specified that it's bouncing off of the electrons. If I have atoms that my light is scattering off of, why would it scatter off of electrons and not, let's say, a nucleus of a, say I have water molecules. I have a hydrogen nucleus, a proton. Why is it not scattering off of the proton? I'll give you the short answer is it does, but we don't observe it. So why don't we observe it scattering off of the proton would be an honest question.
Is it because it doesn't happen all that often? Because it's so small?
Not that it doesn't happen all that often. It probably doesn't happen nearly as often, right? But look at this equation. After doing conservation of energy momentum, you find that the difference in wavelength is inversely proportional to the mass. This number here came out to be 2.43 picometers. And since the mass of a proton is, what is it, 800, let's just say 1,000 times between friends, plus or minus 50%. If the mass of a proton is 1,000 times bigger than the mass of an electron, what does that make the wavelength shift for scattering off of a proton? If you divide by something that's 1,000 times bigger, what do you get?
Small enough.
Something that's 1,000 times smaller. So you could have Compton scattering off of a proton, but this number then would be measured in femtometers instead of picometers. And so you'd have to have a super, super, super precise spectrometer to be able to observe it. So that's why we don't generally observe it. I think people have made some kind of observation of Compton scattering off of protons, but it's very specialized. Okay, so here's the calculation of that Compton wavelength, as we call it. To make life easy, we don't want to do h over mass of an electron times the speed of light every time. And so we can rewrite the equation as lambda prime, the scattered wavelength minus the original wavelength is the Compton wavelength times 1 minus cosine of theta. And once again, what is theta? Oh, by the way, we should all pray for DJ. He's taking the MCAT, I believe, today. You could use some prayers, I'm sure.
Why would you think of this early?
I don't know. What was the theta measuring?
It was the angle between, I don't know, the angle between two things.
It's easy to make a joke about that because that's what it always is, but I know it's the angle between the incident light and the direction it's scattered. So that angle is going to be 0 if it doesn't scatter. If it bounces straight back, it would be pi. Now, if you look at this equation, 1 minus cosine theta, what angle for theta is going to give you the biggest value in parentheses? Now, cosine theta goes between what two extremes?
0 and 1. Oh, wait, I misheard what you said. I know what you meant, though.
Goes between minus 1 and 1.
Yeah.
And so if this goes between minus 1 and 1, what's the maximum you can get between parentheses? 1 minus, a minus 1 will give you 2. So your maximum shift would be 2 times the Compton wavelength. Or basically 5 picometers. Really, really small is the maximum shift you can get. And what would this wavelength have to be to give you cosine theta is minus 1? What is theta if cosine theta is minus 1? So it's 180. 180 degrees, which is pi. So if it bounces straight back at you, if it scatters straight back, that's when you're going to have the maximal shift. Okay, now you have a problem. And notice I put a lot of writing on here, and then at the bottom I said only 2 of the equations I wrote are necessary. An X-ray of wavelength 10 picometers, remind us all, what is a picometer? 10 to the minus 12 meters, is scattered through 110 degrees by an electron. What is the kinetic energy of the recoiling electron? So work on it. Get paper, work on it. It does. That's why we use it.
I think you're on.
So you get it into this. I use this. Okay, my. I'm not fully drinking, but. That was like, wait, why is it empty?
Oh, and then use this for that using this. States in this.
What equations do you use?
This one.
Yeah.
I restated just to make sure.
The what? Yeah, I use that one too.
I need to.
Okay, we've had 10 minutes on this. I'm not sure if anyone has a final answer that is a correct answer. So let's look at our strategy, right? Part of the goal here is once again to recognize the process. And like I said, the problem is mathematically easy, But thinking it through is the hard part. So in my little hint here, you only need a conservation equation. I wasn't specific on which conservation equation because I wanted you to think about that. By a show of, well, not by a show of hands, because I don't want to give it. Which thing are we conserving in this collision? There are two correct answers. Okay, momentum. What else? Actually, there's lots of correct answers, but there's only two that seem relevant. What else are we conserving besides momentum? Go ahead. We are almost conserving mass. Not quite. It's energy. We're conserving energy. The reason we're not quite conserving mass is because some mass is converted to energy and vice versa. And in this process, we're going to have a slight change in the mass of the electron because the electron is changing its total energy. So we're going to start with conservation of energy. So initially, we have energy equals the energy of the photon plus the energy of the electron. So that would be hc over lambda plus mass of electron c squared. That's what we start with. And then we're going to end with that relationship, right? Total energy equals total energy. But I'm going to simplify things a little bit in that my total energy can be broken down into the kinetic energy plus the rest energy. And that's going to make my life easy then, because if energy is conserved, then my final energies have to equal each other. And so if I solve this for kinetic energy, I'm going to have to subtract hc over lambda prime. And I'm going to have to subtract E0. And I wrote so big I need to make a new page. Just don't need two new pages for sure. And so I'm left with the equation from the previous page that kinetic energy is equal to hc over lambda prime minus hc over lambda. And I'm going to go back so you can verify that. I have hc over, okay, so hc over lambda minus hc over lambda prime is what I got there. Somehow I believe that's going to be a negative. I'm not sure why. So now we have our equation to work with. Yeah, really not sure why. Yeah, I'm not sure what I did to get the wrong sign here, but I have the wrong sign. We're just going to get a negative answer and we'll say, well, Richard got the wrong sign. So now I need to calculate what these are. Well, this one we can do right away. I wrote the whole thing out because I didn't want to think about how many digits I need to use. And so we can calculate the energy that our photon had initially. Actually, no, maybe I don't have a sign error now that I think about it. It is correct. Yay. Richard didn't make an error. Let's scratch all of that Richard made an error stuff. So like I said, I did this on a kind of hokey calculator here, so I'm not 100% confident in my number. So Trace, I'll let you give me a correct number. I'll write down what I got, and you can tell me if it's right.
Close enough.
What is it?
1.985.
Okay. Now for the second one, I need to use the Compton scattering equation to find what lambda prime is. So I have my Compton scattering equation. Well, it's written like this, first of all. So we have 10 picometers plus 2.426 picometers times 1 minus cosine of 110 degrees. And this I really, really was not confident in my calculation. That's it. Whew. I'm actually surprised. Like I said, that calculator did not inspire confidence. So my energy of the photon after the collision is going to be Planck's constant times speed of light over this new wavelength. And so since my numbers have been in the ballpark at least, I'm going to write down what I got and we'll see if I'm right this time. Color me shocked. I truly did think they were wrong. So finally, the kinetic energy was equal to hc over lambda minus hc over lambda prime. And I shouldn't have put E prime here because that makes us think of the wrong variable there. I assume since those numbers were right that this one should be right. 4.87 times 10 to the minus 15 joules is how much energy that electron has. Now one might say, would you need, well, a good question, would you need to use relativistic calculations for an energy like this? Is this a big energy or small energy? Okay, compared to everyday energies, this is extremely small. But for an electron, is this a big energy or a small energy? That answer is, it's pretty large. If we want to calculate how many electron volts this is, our conversion factor is just using the charge of an electron. And so that's 30.4 kiloelectron volts. Now, I'm not going to do the final calculation to calculate what the speed is, but we could calculate gamma in 2 blinks of an eye. We can calculate gamma because we know the rest energy of an electron is 511 kiloelectron volts. So gamma is equal to the total energy over mc squared, which is the total energy over the rest energy, which is going to be my 511 kiloelectron volts plus 30.4 kiloelectron volts all over 511 kiloelectron volts. And I didn't calculate this, but we can see what the value is here. If I can turn on the calculator. 541.4 divided by 511 is 1.06. So if gamma is 1.06, there's a 6% error if you don't use relativistic equations, which means it's pretty close to the level of where we'd say you need to use relativity. It'd be on the side where we say relativity generally, but that's how we can check real quick. Right? If gamma came to be 1.0001, I'd say there's no reason to use relativistic equations because it's going to make an error that's like 0.01%. So it's a quick way of checking. So this calculation, not mathematically difficult. The ideas, though, of the energy being conserved and then using those equations, that was the hard part. Any questions about this process?
So this would be like, it's be like a synthesis type of thing?
Yeah, it probably would be in the synthesis category because you had to combine two ideas. All right. Now, almost finishing up the topic, which phenomena support a particle theory for light? So we have a couple of options here, and I just want to go through each one, and you give me a thumbs up, thumbs down. Compton scattering, does it support particle?
Yes.
Yes. Excellent. Rayleigh scattering, does it support particle?
No.
You know, we didn't talk about how Rayleigh scattering works, did we? So I'm just going to cross that one out because we didn't talk about it. I do believe the answer is no, but I actually have to look it up because we didn't talk about it. Photoelectric effect. Okay, I got a bunch of thumbs up on that. Young's double slit diffraction. Right. X-ray production. Excellent. It's important to recognize that we have these, and then we have to deal with what does this mean. So how do we deal with this as physicists? We say, and yes, I consider you now physicists. You've gone through a lot of physics training. What do we say the outcome is? What is light? It's both. In any situation you look at, for a specific thing, it's going to be one or the other. But in some things like, well, this photoelectric effect experiment, we didn't do this, but I have another set of equipment where we use a diffraction grating to separate the colors from the mercury vapor lamp. Is that a wave or a particle nature using a diffraction grating? Wave. But then you're doing the photoelectric effect, is that a wave or particle nature? That's particle. So that one experiment is using both the wave nature and the particle nature in one experiment.
So
It doesn't give us as good a result. That's why we didn't use that equipment. Go ahead.
So then, because we're using both, we just say that it supports both, or what?
Well, we say light is both.
Yeah.
And so in that experiment, you would say for this part of it, it was a wave. For this part of it, it was a particle. Now, we're going to shift to quantum physics. So this is our transition from waves and light to quantum physics. So we start with, when I have light traveling through a diffraction grating, let's just go with the double slit. We do double slit because it's the easiest one to wrap our minds around when we're looking at the outcome. The diffraction grating was easiest when we're doing the experiments. So if I shoot a single photon at my double slit, what's going to happen when the photon gets to the double slit? Start with, when it gets to the double slit, is it going to behave like a photon or like a particle or like a wave? Okay, it was a particle when I shot it because I said a single photon, but when it gets to the double slit, that is a wave nature experiment. And it's going to behave like a wave. Now, you might say, wait, you're just down to one photon. If it's a wave, when the wave goes through the slits, it interferes with itself. So one particle, if you want to think of it as a particle, which like you said, it's a wave as it's going through the slit. You say that particle went through both slits. If you think of a wave, it's not a problem. Because the wave has a width. You come and you have the two slits, and the part of the wave that hit this slit goes through, the part that hit this slit goes through, and it's not a problem when you think about it as a wave. You think as a particle, it's a lot harder to say, but how's the particle going to go through both slits? The BB can't go through both holes, one or the other. When we detect these, we detect the photon again. Our detectors are photon detectors. And so if you shoot one photon through a double slit, and you have a screen back here, it's only going to make one blip on the screen. So you might have a blip here. And then I do it again, I might have a blip here. Do it again, I might have a blip here. Do it again, I might have a blip here. And so you get all of these blips. And so if you just do it like 100 times, oh, I don't have that picture up here. Nope, it's this way.
What do you mean when you say blip?
Where the photon hit. I'm going through there's a whole bunch of important stuff. So here's what you got. Now this has electrons because I don't have a picture to go through. But people have done this with photons, shooting single photons. And with 40 photons, you get some pattern here that if you only looked at the top line and didn't see the others, it'd be hard to differentiate really what the pattern is. It kind of looks random. But as you get 200, you can start to see, okay, there's definitely gaps here. You get 2,000, it becomes clear, okay, it's more dense in the middle, fading off to the gaps. And if you did a few million, you would see the standard diffraction pattern. So I said, if you did this, it has been done by scientists. And they have verified that even if you're shooting single photons, that you get that diffraction pattern. I have to go all the way back to where I was because that picture I took out of sequence. So this diffraction pattern is a sign of behaving as a wave. And of course, you probably saw where I'm going by the caption on that other slide. As we move into quantum physics, I love these quotes because they illustrate something that should be resonating in your heads. Richard Feynman, or well, start with Niels Bohr. Anyone who has not been shocked by quantum mechanics hasn't understood it. I saw something on Quora just the other day that talked about quantum entanglement. And he says, why do people talk about this as hard? You have two boxes, one has a black ball, one has a white ball. I open the one with the black ball, I immediately know the other one has the white ball. What's difficult about that? Person responded, well, clearly you missed the entire quantum mechanics thing. You don't understand it at all. So if it seems simple, you don't understand it. If it seems too complicated to understand, yeah, you're probably getting it. Okay, I know that's a little simplistic because if I had my 10-year-old grandson here, it would seem incomprehensible to him and he wouldn't be getting it. And now, Richard Feynman's quote, I'm going to tell you what nature behaves like. If you'll simply admit that maybe she does behave like this, you'll find her a delightful and transient thing. So basically saying, if you kind of put some faith out there, it really is interesting. But it's going to take some faith, right? Science takes faith. Religion takes faith. They take different kinds of faith. So let's head into it. Got 10 minutes. Probability. Now, I'm going to point to Chad a lot because he's also taking quantum mechanics at the same time. So he would have been really nice for him if he could have had this before taking quantum mechanics because it would have given just a little bit of a toe in the door. When we're dealing with quantum mechanics, we're dealing with a probabilistic system. It's all probabilities. It's not deterministic. Deterministic is everything we've done. Everything we've done has things like, I take this bar, I let go. What's it going to do? It's going to fall. Absolutely, right? Quantum mechanics is saying, well, there's a this percent chance it'll fall and a this percent chance it'll do something else.
Stats.
Yeah. And so quantum physics says we can't know exactly what's going to happen. Even if we know all of the parameters, perfect infinite number of decimal places, we still can't predict exactly what's going to happen. We can only talk about the probabilities. Now this causes some consternation. So you guys might have seen that famous quote by Einstein that says, I don't believe that God plays dice with the universe. That quote, now Einstein may or may not have believed in God. It depends on what day of the week you asked him, I think. But what he was saying there was talking about quantum physics and this probabilistic nature. He basically had the feeling that we're wrong if we believe we can't determine what's going to happen. We are mistaking our ignorance and saying that our ignorance is good physics. But quantum physics says that no, really, we can't determine what's going to happen with certainty. We can only determine probabilities. So God playing dice with the universe is that God here is nature, and the universe is our physics, that nature is random rather than, well, it's not random, but probabilistic rather than deterministic. That's what his quote was about. So, once again, if a mind like Einstein's is having some real serious issues with the concepts of quantum mechanics, it should be no surprise that a mind like mine also has some issues with quantum mechanics. So, let's move forward a little bit. Probability. When we talk about light, when we did the diffraction pattern, we could say, okay, where it's really bright, the probability of the photon hitting there is larger. And where it's, not no light at all, the probability of the photon hitting there is 0. And so the intensity of the light tells us about the probability of the photon hitting each place. Does that make sense? That the intensity of the light, how bright it is, tells me what the probability of light hitting there is. Now, if we treat light as a wave, which of course it is when it goes through diffraction grating, then we have the intensity of the light is proportional, well, intensity is energy per time area. So it's the energy per second hitting some amount of area. And that's proportional to the electric field squared. Now, it's really unfortunate. The reason I used energy up there and E here is so I don't have E standing for the same thing. But this here is the electric field squared. So we can come up with an equation for the electric field that you get on your screen, and if you square that, it will then tell you what the probability of the photon being found at that location is. And once again, I have to stop. Does that make some sense?
Sorry, again.
So we have light hitting a screen, and when the light hits the screen, we have an intensity pattern. And we say this intensity pattern is telling us the probability. So here it's high probability that I will find a photon there. Ability. And here it's low probability. Or 0 probability, actually. But then from doing math, this here is the electric field squared. And so if we take the electric field squared, that tells us the probability of the photon being there. It's actually a really important concept to quantum physics, because we take that and we say, and this is just the math to go with what I just did. We take that and say, okay, we have what we call a wave function. The wave function is the electric field as a function of position and time. And if I take that wave function and I square it, that equals the probability. This concept is a concept then that's going to transfer into quantum mechanics. So what aspect of the electric field, which is our wave function, gives the probability of us finding the particle, the photon? at a given location. So it was electric field. What gives us the probability? What did you say? B? B is correct. It's the square of the electric field, the amplitude of the electric field. So it's the amplitude squared. Now in 1923, Louis de Broglie said, hey, if light can be both a wave and a particle, then other particles should have wave properties too. And so he put that out there, and he calculated that the wavelength should be Planck's constant divided by momentum. Where does this come from? Well, it comes from the relationship between wavelength and Planck's constant and momentum for light. So Louis de Broglie says this. Erwin Schrödinger reads about this, and he goes and he gives a seminar about Louis de Broglie's new idea. By the way, when I was in college, my teacher said de Broglie. I was called de Broglie, and then I learned it was de Broglie. Last year I taught quantum physics at Southern, and I was really surprised that when I said de Broglie, they were like, yeah, that's how their teacher taught them to pronounce it. So it is de Broglie, even though in English it'd be de Broglie. And Trace, you better be with me on this.
Yes.
Okay. So Schrödinger said, wow, just imagine that electrons could behave like waves. And, what was it? Peter Debye says, oh yeah? Well, if electrons behave like waves, then shouldn't you be able to have a wave equation that you use to find the wave function for an electron? Schrödinger was like, yeah, you're right, I should. And so Schrödinger went to work, and he came up with a wave equation from which we can find the wave function for an electron. And thus quantum mechanics was born. Now that's one of the two origins for quantum mechanics. The other origin of quantum mechanics comes, and this is actually going to something else, comes from Erwin Schrödinger. Not Erwin Schrödinger. That's the one I just said, right? From Werner Heisenberg. Werner Heisenberg was trying to figure out where the electron is in an atom. You may have seen atomic orbitals and s orbitals and p orbitals and d orbitals and whatnot, and thought that's where the electrons are. I mean, I know when I was in high school we saw them doing circles, right? Wrong! And Heisenberg was like totally frustrated. We can't figure out where the electrons are. We have no way of knowing. So he's like, forget that. Let's look at what we can know about electrons. He started classifying, okay, so we can measure this observable like, it's energy. We can measure this observable, it's magnetic moment, and so on. You start classifying these, and that's what gave us another way of doing quantum mechanics using matrices. So, and hey, look, it's time. Well, we'll talk about Davison-Germer experiments Monday. Have a great alumni weekend. Happy Sabbath. Question?
Test next.
Is our test next week?
Yeah.
Yeah, I think that's right. I do not believe our test is next week. I sure hope not.